Welcome back once again. This is LearnRite. We are still in the business of making you happy. We just want to focus on you and make sure that you learn it the right way and pass your exams, go to the university, and of course, do the course that you cherish. Come out to become the person that you want to be. That is the main business for which LearnRite was established. Now, we are still on chemistry. We're looking at bonding. Bonding, the topic that tries to explain what nature is almost all about. The force of attraction that exists between various substances, and therefore that makes life to be in a continuum. In fact, bonding to some of us is the reason why life is in perpetuity. As we talk about some of the bonds that exist between various substances, I guess you will agree with me on this statement. Now, we have looked at the first two types of bonds, the ionic bonds. We have looked at metallic bonds. Now we are on covalent bonds. And for each of the bonds, remember that we said we're interested in 5 things: the nature information, the units of current lattice size, the intermolecular forces existing between the molecules or the substances of that particular bond, and then, of course, examples and the physical properties. So when we came to covalent bonds in our last video, remember, we have discussed the nature information already. And what did we say about nature information? All we said was that covalent bonding is all about sharing. It's about sharing of an electron pair, where 2 atoms will come together. Each one will donate 1 electron. We get an electron pair, they will share. And after the sharing, each of the atoms will assume a complete electronic configuration, or an inert gas electronic configuration. They will either complete their doublet and become happy, or they complete their octet and become happy. So we said that covalent bonds normally is formed among the elements that start from group 4 to group 7. Group 4 elements, because they are in group 4, have 4 electrons in their atomic shell, and so we need 4 more electrons to fill their octet, and therefore can only form 4 bonds. We said that group 5, being group 5 has 5 electrons in the atomic shell, they need 3 electrons to fill their octet, and therefore they'll go and share 3 electrons. In the process, form 3 bonds and become will have their octet complete. Group 6 will share 2 electrons because they need only 2 electrons to fill their octet, and they'll form 2 bonds. Group 7 will always form 1 bond because they need 1 more electron to fill their octet. Group 8, remember, they already have their octet fully filled. Very stable electronic configuration, and so they hardly take part in any reaction. They don't react at all because they are always stable. That is what we talked about covalent bonding. We saw the number of bonds that were formed for carbon, for instance, forming 4 bonds. We saw it for nitrogen forming 3 bonds. We saw it for chlorine forming 1 bond, and several others. Now today, we are going to look at our second focal point. That is, if I take B, I'm looking at units occurring at lattice site. That is the second thing we need to know under covalent bonds or covalent substances. In the course of this discussion, I may be adding intermolecular forces because they go hand in hand. They go hand in hand. Now, before we can look at units occurring at the lattice site of covalent substances, in other words, when we take X-ray diffraction of the solid forms of covalent substances, what are we going to see at the lattice points, at their resting places? What are we going to see? Before we can define this or understand this substance that occur at the lattice site of various covalent compounds, we need to establish that there are 2 types of covalent substances on Earth. We have 2 types of covalent substances. We have I, or 1 molecular covalent substances, and then II, we have giant covalent substances. Now, molecular, or some people call it simple covalent substances, what are they? In fact, on Earth, they are the substances that exist the most. Almost all the compounds that I explained in their bond formation, from the group 4 to the group 7 elements, the types of compounds that they form, most of them are molecular covalent substances. They are simply small substances that consist of a few same molecules. Because if you say substance, if I talk about water, I'm talking about water molecules alone existing in that large form. This is an example of a glass containing water. You see all the water together there. I'm not seeing individual water molecules, one in this glass. It's put together. This is alcohol. It is together. So we have several millions of alcohol molecules that come up to fill this. Just as in the same sense, we have several water molecules, millions of water molecules that form or that occupy this space here. Now, because they are together, it is telling that there is some form of force that is holding them together. Now, if you take an X-ray diffraction of these things, what are you going to see at the lattice point? That is what we are interested in. That is what our focus is now. So, almost all simple substances that are small in size, of the same types of molecules, held together by certain type of intermolecular forces. In fact, in simple covalent forces, they can have two types of intermolecular forces. We'll come to explaining them better when we come to the next video. In this simple covalent substances, they either have hydrogen bonds as the forces holding the individual molecules together, or they may have what you call van der Waals forces holding the individual molecules together. But the simplest thing that I want you to know is that just by the name, molecular covalent substances or simple covalent substances, we say they are small in sizes. And they are held by a few of their kind of molecules. They cannot form huge substances. Now, I want to tell you that they cannot form huge substances because the intermolecular forces that is holding these individual molecules together are not very strong. So as they become huge, as they become big, it weighs on some of the intermolecular forces, and then they will do what? They will break. And so they can only form small group of such substances. In simple terms, when we want to define it, we say molecular covalent substances are small substances that consist of few same molecules. Few same molecules. So water. But the water molecules may be about say million, but it cannot be as huge as we will find in giant covalent substances. So they contain few same molecules, and they are held together either by hydrogen bonds or van der Waals forces. When we come to treat intermolecular forces, you will see that hydrogen bonds and van der Waals forces are the last type of, or the weaker types of intermolecular forces that we have. And so because the intermolecular forces there are a bit weak, they are not, simple covalent substances are not able to combine to form very large or huge molecules or substances. On the other hand, giant covalent substances are huge. They are huge substances that consist of many of the same kind of molecules, and they are held together by covalent bonds too. Please take this. The giant covalent substance, if you take 1 mole of the substance, atom, as forming 1 mole, are all held by covalent substances. Let me explain that here. Let me use one example. Silica, SO2. I've not come to examples, but let me use that. SO2 is one of the giant covalent substances that we have. Silicon bonded to oxygen. That is just 1 molecule. That is just 1 molecule. But again, silicon can again be bonded to silica can also be bonded to another one. This silicon can also bond to another oxygen molecule, like that. Now, if you take this is 1 molecule. If I take this is one molecule, silica. Okay, this is also another molecule, silica. But look at this molecule and that molecule here. This silica, SiO2, can be bonded to this silicon 2 by another bond here. These bonds can be seen as intermolecular forces, but what are they? It is also a covalent bond. So in giant covalent substances, the bond holding the individual molecules are covalent, and the bonds holding the atoms within each 1 mole of the molecule is also what? Covalent. In short, the intra, that is bonds within 1 mole, intra, and the inter, bond between 2 molecules are all what? Covalent. In other words, there's no distinction between the bonds within a molecule and the bonds between molecules. They are all covalent. And so because covalent bonds are sharing of electrons and they're strong, then it means that these atoms can form several of such covalent bonds and they are all strong. So it can form and increase and become very, very large. That's why we call them giant covalent substances. Giant covalent substances. So molecular covalent substances that's one. If I take this, you can think about, apart from silicon, from carbon, nitrogen, group 5 onwards, almost all the covalent compounds that they form will all form simple or what you call molecular covalent substances. Several examples: water, HCl, carbon dioxide, carbon monoxide, ammonia, HF, oxygen, hydrogen. I mean, all these are all what you call simple or molecular covalent substances. Simple or molecular covalent substances. They can come together and form various quantities, just like we have seen in water. But they cannot continue to form very giant molecules as compared to giant covalent substances. Why? Because if I take water, one water and another water bonded together is a bond we call hydrogen bond. It's not so strong a bond to let the water to continue to hang on its own. I mean, one water molecule to another molecule. Though it's quite strong when it comes to, it's the strongest among the weakest. If you take carbon dioxide to another carbon dioxide, as for that one, the bond there is very, very weak. It's a van der Waals force. That is why when you have carbon dioxide cooked in this, it's a gas. That is even the reason why it is a gas. Because they are not, the bond between one mole of carbon dioxide and another mole of carbon dioxide is weak. So they are not able to come so close together for them to exist in the form of what? A liquid. The bonds in liquids are stronger than the bonds in gases. And the bonds in solids are also stronger than the bonds in liquids. So if you have carbon dioxide gas here, as soon as I remove it, because the bonds between carbon dioxide molecule are weak, each one the bonds will start to break and they will move their separate ways. So for giant covalent substances, we have various types. Let me give those examples here. We have what we call diamond. Those are the examples. We have diamond. We have another compound called graphite. We have plastic, etc. What is diamond? Diamond is simply carbon atoms bonded to each other several times. Have you seen one before? Diamond. Look at the women, the rich ones. You tell, look, my ring is a diamond ring. Diamond is something that God created and is used as jewelry. Very nice. We have various types of colors. The very pure white ones are very, very nice. Some are light blue, some are light green. Very shiny, sparkling. Well, in chemistry, what is it? In true nature, what is it? It's simply carbon atoms bonded to each other several times. Remember, we said carbon is in group 4. So each carbon atom can form 4 bonds. Each carbon atom can form 4 bonds. So if I have this carbon here, and it forms 4 bonds, 1, 2, 3, 4, another carbon here can also continue to form the 4. So this carbon is bonded to, this carbon is 1, 2, 3, 4 bonds. Another one can come here, it can form its 4 bonds. So 1, 2, 3, 4. and then it will continue like that. And when you have such carbons bonded to each other several times, depending on the types of bond, there are some slight arrangements, difference in bonding. It is either diamond or graphite. Diamond and graphite are all giant covalent substances, but they have different spatial arrangements of their covalent bonds. Diamond having a more compact spatial arrangement, and so it is hard, very hard. We don't have diamond as an example here, but for graphite we do. Graphite, if we take this pencil, that black thing in it that we write on paper is made of graphite. Okay, that is what I've taken here. That is the example I've taken here. I mean, it's removed here. So this thing here is graphite. We'll give you a better picture on the screen. This is graphite. And graphite is also carbon bonded to each other, carbon several times. But in between layers, the bonds there are long, they are weak compared to that of diamond. Diamond doesn't have what we call layers. As for diamond, this is how it is. This is an example of diamond. Let me show it to you. If I take this carbon holding me here, each black thing you see here is carbon. Each one is bonded by 4 times, by 4 other carbons. If I take this one, for instance, this is 1, this is 2, this is 3, and that one comes here, 4. If I take this one, this is 1, this is 2, this is 3, there's a hole here, which can go here, making it 4. If I take this carbon here, I have 1, 2, 3, one can go out here, 4. If I take this one to 1, 2, 3, and 4. Each carbon atom. So this is how carbon is. Anyhow you take it, it's the same way. So look at this side here, for instance, this shape. That is how diamond is arranged. Each carbon bonded to each other by 4 other carbons. And remember, when we're doing I was doing in my last video, I explained this. That is carbon bonded to 1, 2, 3, 4. But here, instead of, if it is diamond, this one should have been carbon. But this is methane, CH4. That is why we have the hydrogen atoms at these ends. So this illustrates the tetrahedral nature of carbon. So in diamond exhibits that tetrahedral nature. Each carbon bonded to 4 other carbon atoms in diamond, making it have a very compact and strong shape. In fact, in the days past, people thought that diamond was the strongest substance, but another substance has been identified, which has a similar structure, which they say is stronger than carbon. So in corpus series, it is indicated there that it was probably thought to be the strongest. It is no more the case. We will correct it. Okay, so that is diamond. Diamond is simply written as CX. Diamond, the formula is CX, where X is the number of times of carbons bonded to each other, or you can say CN. Okay, again, graphite is also the same thing, CN, also the number of this. But when we come to do solids, I will tell you the difference between diamond and graphite, where the difference is. It simply lies in between their spatial arrangement. So, giant covalent substances, diamond, graphite, plastic, that is plastic we have here. And then this one, of course, this is silica. Let me show you to silica, the powder. That is a powdered form of silica. Usually, people will call it POP in the building industry. You see some buildings, the roofing, the ceiling of some buildings. And because it is also giant molecular substance and the bonds are strong, when you mix water with it, it forms a very hard substance. And it's used to seal our rooms where nothing can penetrate. Okay, where nothing can penetrate. And that is also what they use in making the POP. When someone injures or gets a fracture, they mix it there and make sure they use it to straighten the bone. That is made of silica. So silica, SiO2, silicon dioxide, is a giant molecular substance. Diamond is a giant molecular substance. Graphite is a giant molecular substance. And plastic is a giant molecular substance. For simple molecular substances, almost all other substances are simple molecular substances. Now, we have defined the 2 types of covalent substances. We're saying that the simple or molecular covalent substances are simple and they are small, of the same types of molecules and held either by hydrogen bond, that is the intermolecular force, either hydrogen bonds or van der Waals forces. But for giant covalent substances, they are huge substances of the same molecules. They are held together everywhere by covalent bonds. Now, having known the difference between these two types of substances, now let's look at what you see at the lattice site. What does X-ray diffraction show us at the lattice sites of these substances? For any molecular covalent substance at the lattice site, if the molecular covalent substance is water, for instance, you will see the water molecule itself. You will see the water molecule itself. If the molecular covalent substance is carbon dioxide, you will see the whole of the carbon dioxide molecule. If it is oxygen, you will see the whole of the oxygen molecule. If it is HCl, you see the whole of the HCl molecule at each of the lattice sites. I repeat, for molecular covalent substances, X-ray diffraction will give you at the lattice site the whole molecule itself showing. On the other hand, for giant covalent substances at the lattice site, X-ray diffraction will give you the atoms of the molecule of that substance. So in diamond, an X-ray diffraction of diamond will give you at the lattice site carbon, 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 carbon. An X-ray diffraction of silica at the lattice site, you either see silicon or you see what? Oxygen. So for giant covalent substances at the lattice site, you see the atoms of that giant covalent substance. In molecular covalent substances, you see the whole molecule at the lattice site. Let's see an example on the board here. The lattice site of water, an X-ray diffraction of water gives you something like this, as we see on the board. You see here, the whole of the molecule of water, H2O. This HHO. Whole of the water there, the whole of the water there, the whole of the water there, the whole of the water there. So at the lattice site of molecular covalent substances, you see the whole molecule. At the lattice site of giant covalent substances, you see atoms of the molecule. I hope it is well explained. So I only wanted to talk about these are kind of lattice sites, and then of course let me quickly add in Damluga. Well, let me summarize it here. At the lattice site of giant covalent substances, please, what do you see? I am saying that, or chemists have found out that you see the individual atoms of the giant molecule. At the lattice site of molecular covalent substances, scientists have proven that you see the whole molecule. So be careful. The question will tell you, what will you see at the lattice site of hydrogen molecule? Don't go and say you see molecules. Say you see hydrogen molecules. If you say you see molecules, you'll be background, because the name of the molecule has been mentioned. At the lattice site of hydrogen chloride, what will you see? Don't say you see molecules. Say you see hydrogen chloride molecules. At the lattice site of graphite, what are you going to see? You say you see carbon atoms. At the lattice site of silica or silicon forza, what are you going to see? You will see silicon at some lattice site and you see oxygen at some lattice site. That is it. Thank you so much for being with us. Let's go on. We'll move on to the next video and then we'll explain the others. Thank you.